with type 3, but it's not too common at this moment. So the other part of the talk is that when we design fuzzy systems, we need optimization, because for real applications, the fuzzy system needs to be optimized. So in this regard, we have been using bio-inspired or nature-inspired meta-heuristics that can help us to design optimally these fuzzy systems for applications in many areas. In my case, it's mostly in control, but in my group are people working on pattern recognition, time series, and other medical diagnosis and other areas. I collaborate with them, but it's not my main thing. My main thing is in controlling robotics. And anyway, we have these type 1 and type 2 fuzzy models in many cases, and we need optimization in any of those situations, because fuzzy systems may be difficult to design. I mean, parameters, we need to find the optimal parameters and sometimes even optimize the number of rules and the structure of the fuzzy system. But still, the question is, maybe there are problems even more difficult than the ones that we have solved up to the moment. So maybe we need higher types or higher orders of fuzzy models. So in that regard, most of the interesting research theoretical research being done right now is on finding these different types or orders of these fuzzy models, or combinations of fuzzy with other ideas that you can find in the literature. But the main motivation is that we have problems that are more difficult, maybe in the future even more new problems that will arise that will require higher types of models anyway. So the main question is that we have to do research on this. Even we have other kinds like intuitionistic fuzzy models, like I know Professor Atan and Fatih work mostly on intuitionistic. Type 2 has been combined with intuitionistic with good results. So combinations of different kinds of extensions or augmentations of the original ideas of type 1 can be interesting. But here the main contribution is showing how we can obtain these fuzzy systems, in particular type 2, with optimization for some problems that I will illustrate with these problems, what I have done. So mainly the idea is that we need to minimize the error between the output of the fuzzy model or fuzzy system with respect to a real system, a real dynamical system. And so the difference is in some metric, we can measure with some metric the difference between the results of the fuzzy model and the results or the values of the variables of the real dynamic system. And if we minimize this difference, then the fuzzy model will be a good solution or a good approximation to the real system. So coming to the beginning, then type 1 fuzzy sets were an extension or in some way a generalization of the original idea of classical sets. So the extension was providing an interval of values of membership between 0 and 1 instead of only having 0 and 1. So in classical sets, we only have true or false, a membership of 0 or 1. And now Professor Sade proposed in 1965, and he proposed that membership can be any value any real value between 0 and 1. And in that moment, then this idea of a fuzzy set was proposed. And that was not at that moment considered type 1, but we now view it as type 1 because further in time later, we did find that other authors and also even the same Professor Sade, he proposed type 2, and in that case, the membership is not a number, it's a fuzzy set. So that's the difference. Instead of having any value between 0 and 1, now the membership can be fuzzy. That's why it's called type 2 in that sense, because the reason was that we cannot sometimes we are not able to give a precise value to this membership. That's the main reason. So here is an example very quickly, just for the ones that maybe are not familiar with type 2. This is a type 1 fuzzy set, of course, for the concept of tall, meaning the tall people. So if we assign a membership function like this one is a type 1 membership function, a triangular one, for the concept of tall, then for any particular height in the x-axis, then we will have a membership of belonging to this set according to this particular height of 1.8 meters. In this case, if this is the right way to define this concept, then we will have a membership of 0.62 of belonging to this set. Of course, we have the problem that this is really not a good way, because this will be in some way arbitrary, as this is a subjective concept, and the meaning of this word is different for different people. And so the membership function maybe for me could be this one, but for you, I mean, every one of you could be different. So in some sense, this is like an arbitrary function, not representing the difference in the meaning that people have about this concept. So that's why type 2 did arise, and because we have this problem. And of course, this is an improvement of just saying if the person is tall or not tall, which is the way that it was done in classical sets, but it's not really representing the uncertainty of the concept, because it's just giving a precise number to the membership. So it's like representing only the vagueness of the concept, but not uncertainty in completely represent the uncertainty of the meaning of tall. So what people did was at the beginning propose interval type 2 fuzzy sets, in which what they proposed to do is use an interval around 0.62 to represent the uncertainty of the concept. So about 0.62 will be represented by an interval. Then the complete definition of general type 2 fuzzy set is assigning a fuzzy set to the memberships, not just an interval around this number. So a fuzzy set will be used for representing this membership for any element in the interval of 0, 1. So the mathematical definition is like this. So we have a set A, and we have the elements. We have the primary membership function, and then a secondary membership function. But in the case of interval type 2 fuzzy sets, the secondary membership function is assumed to be 1, fixed or uniformly 1. And so we have just intervals. In the case of a general type 2, we will see that we will have here another function, really another function, because we give different membership to the different points in the domain of U. So not a fixed value. But this is something, even in this case, something that can give good results. And many people that say that they are doing type 2, many of them are just doing interval type 2 because they are using this model, but it's a better approximation than using type 1, of course. So in this case, Mendel and John did find out that upper and lower membership functions will represent in a good way these kinds of interval type 2 fuzzy sets. So in this case, the improvement is that, for example, in the case of the example of the concept of tall, now we don't have just a simple triangular like the dotted line inside here, but we are having many interval type 1s inside this area. And this area is called the footprint of uncertainty. And we have an upper membership function, which is the highest here, and a lower membership function, which is the one below here. And inside this upper and lower, we have an infinite number of type 1 membership functions embedded inside this type 2 triangular membership function. But this is representing the difference in the meanings, because, for example, this triangular maybe is my interpretation of tall, but other type 1s, other triangulars inside, type 1 triangulars inside, are the meanings of other people contained in this representation of the fuzzy set in this case. So this is an improvement, an extension, or an augmentation of the original type 1 concept. And the general type 2 will be using the third dimension to have really a different membership. In that case, we need the third dimension, because here, basically, as the secondary membership is uniform, we don't need to represent the membership coming out of the screen in this case. But in the case of general type 2, we need the third dimension to represent that the non-uniformity of the secondary membership function. But in this case, for any particular height, then we will have, instead of 1 point or 1 value for the membership, we will have an interval. So for this height, then this interval will represent the membership that this height has in the concept of tall. So it's like an interval in this case. So what we have with this extension is that the falsification is like this. Instead of using simple type 1 membership functions. And then we need at the output of a fuzzy system, we need the defalsification. And the defalsification, in this case, is not just the centroid, for example, or the typical defalsification that we have in type 1. We need to have two steps in some way, type reduction and then the classical defalsification that we have in type 1. And type reduction is a kind of a weighted average over the type 1s inside the area, the footprint of uncertainty. And fortunately, one moment in history, Mendel and Liu discovered that we can use only two type 1s to represent the interval type 2. But these two type 1s that we need are in some way not simple ones. And we need, for example, the red membership function is part of the upper, and then we switch to the lower membership function. So the red membership function, the red type 1 membership function is this red one, which is a part of the upper one, and then we switch to the lower one. And the green is part of the lower, and then we switch to the upper. And if we are able to find these two switch points, then we will have completely defined the two type 1 membership functions that we need to have to be able to defalsify this type 2, interval type 2 fuzzy set. And these originally were proposed to be found by using an iterative algorithm, the Karnik-Mendel algorithm. And basically, in many applications with 4 iterations of this algorithm, we were able to find a good approximation to the points, and then we can do some kind of an average to using these two type 1s to approximate the interval type 2. And that was the good thing, and that created around the year 2005 and 2006 originated that we were able to apply it to control, for example, and other applications. And this was very important for us to be able to see also that the results of type 2 can improve over type 1 at that moment. So this is Karnik-Mendel algorithm, which is an iterative. Now we have many other algorithms, and also in some cases we have been able to produce exact mathematical formulas to calculate an approximation of the type reduction. So it's more easy and more quicker now that at that time. But historically, this has been very important. So anyway, at the end, the summary of that, the structure of an interval type 2 fuzzy system is like this. So just all of the elements, almost all of the elements is the ones that you may know for any fuzzy system, even intuitionistic or other kinds of fuzzy systems. So we have the falsifier, we have the fuzzy rules, we have inference. In this case, it's a little different, but similar. And the output is the main difference. We have a type reduction module, and then we have defalsification. This is the part I was explaining, where we may use the Kernighan-Mendel algorithm or another approach. And there are also some approaches in which the two parts are comprised into only one, and we directly go to the output by using some kind of an approximation of this. So there are different ways to improve the quickness of the calculation or the make it faster and for real applications. Anyway, so general type 2 is like this. So we have, instead of having uniform secondary membership function, we have really now a function. So we have the primary membership and then the secondary membership, which is not in this case fixed to one. So we have another membership function. So this is a representation of this. So before in interval, we only had this plane because we didn't need to represent the secondary membership function as it was fixed. Now we have this secondary membership function, for example. So for any value in this interval, now the secondary membership is not the same, it's not uniform. So in this case, we have more complexity. I mean, computational complexity, because now we cannot use the approximation of just finding two type 1s to approximate the interval type 2. We are, in this case, in some way we need to use a sample of this, in some way discretize this interval and use many parts of this secondary membership function, for example, with alpha planes or with vertical slices. So there are several approaches. Anyway, we approximate and we need more calculations. So that's the main problem, how to calculate very efficiently this approximation of the general type 2, because we have an infinite number of embedded, in this case, interval type 2 fuzzy sets inside the general type 2. Anyway, so we have a lot of things that I will not discuss in detail here because of time, but basically we have a generalization of the union, the intersection, all the operations of fuzzy sets, and the implication, logical implication, fuzzy relations, fuzzy functions, and all mathematics can be generalized with these ideas, also with intuitionistic ideas has been done. But this is not a talk on fuzzy mathematics. In this case, just I will say that we have this generalization, and this is inside, even in the case of just using a fuzzy system, for the logical implication or for doing the reasoning, we have these operations inside being used. And this is another interesting part of these things. So anyway, on the application side, I will move to that because of time. At in the decade of 2001 to 2010, it was important at one moment to show that type 2 can be done faster and can improve results over type 1. Because if type 2 was better than type 1, but this was too slow, then we could not use it in the applications, in control, for example. So we needed to do it very fast and also show that type 2 can outperform type 1. So basically, we here are explaining why it was important to to use this type 2 because we have many sources of uncertainty in, for example, in control on the part of the model, on the part of the perturbations, on not having complete information and so on. That's why I'm explaining here. And this is just the motivation that we had for doing this. But let me show you some results. Consider a simple case in control, which is using just the error of a variable in the change of the error. For example, in the error in velocity and the change of the error in velocity, for having a way to calculate the output to control, for example, a vehicle, for example, for controlling the accelerator. So if we want to have a particular velocity, we have to perform a control based on the error and change of the error. On the left, we have type 1 membership functions. On the right, interval type 2 membership functions. So we will see in the results that with these functions, the error when we are controlling, in this case, the system, the errors are lower when we use these interval type 2 membership functions. So let me show you this. This is the representation. We have here the plant or the system. And we have here a type 1 or a type 2 fuzzy controller. And so here in the feedback loop, we assume that we have noise, which is the uncertainty that we have, but we can have also noise here or in other parts of this loop. Anyway, if we have noise in this, sending this signal from the output to the input to calculate the error and then the change of the error, then type 2 will do a better job than type 1. If we assume that there is no error here, an ideal situation, which is not real, not really happening in the real world, of course, then type 1 is sufficient. But if we have noise, perturbation of something in this control process, then we will see in the results that type 2 will be better. So here is a system, nonlinear system representing the plan, and here is the noise that we are assuming that we have here. These are the metrics of control they are usually used, the sum of the square of the errors or the absolute value of errors or time multiplied by the absolute value of the errors. These are three usual metrics of used for the controllers. And we compare an ideal situation where when there is no noise or no uncertainty, and we compare type 1 against type 2, and we will see that there is not significant difference. But if we have a real situation in some way, we assume that we have noise when we send the signal from the output to the input, then when we compare the results of type 1 and type 2, we will see that there is a difference. And here we see the case of no uncertainty, or considering that there is no noise. And in this case, we can appreciate that there is some difference, but not significant. So type 2, which is the red one, the signal of the red one, is showing even in some cases higher error than type 1 because no need for using type 2. But if we have uncertainty, then we can see clearly that the red in the lower figure is more dramatic. The red signal, which is the type 2 result, the errors for type 2 are significantly lower than the blue ones, which are for type 1. And this was for one particular level of noise. We published this around 2009 in Information Sciences. And one of the first papers to show this at that time in that publication. And it was approved. We also did it for different levels of noise. And of course, if there was more noise, difference were bigger. And if noise was reduced, then both signals for type 1 and type 2 were very close because no need to use type 2. And here in the table, you can see the more numerically that we have a lower error with type 2 than with type 1 for the different metrics. and also with the signal following the signal with the type 2 controller, we are closer to the signal than with type 1. That's why the error is lower. So anyway, this is just a summary of what I have said. So that was very important. Then later it was shown in real systems. There is a very nice paper by Hagras, for example, where they did a similar thing, but with a real robot at that time, around the same time that we showed these simulations also. So later we have done it also with real systems and other people. But the thing is that we can show that type 2 can give better results. But the thing is to be able to do it very quickly, because we have to do control in real time. If we are not able to do it very quickly, then it will not be really usable. So interval type 2 was very, very fast. Then the problem was general type 2, as I was saying, because it requires more calculations. We also developed some software for doing this. At that time also, there were no available toolbox for type 2 in the MATLAB software. So we developed our own toolbox in MATLAB for doing interval type 2 calculations, and it's similar to the one that we had in MATLAB for type 1. And of course, here the part of the problem is that in interval type 2 even we have more parameters, because you can see here, for example, this triangular, instead of just having 3 parameters A, B, C, now we have A1, A2, B1, B2, C1, C2. So we have double number maybe of parameters. So the problem of designing this is more difficult. That's why we need even more here optimizing the fuzzy system. So here we have also Gaussian with more parameters, and we have the same interface that you can find for type 1 and in the usual toolbox of type 1. Now MATLAB has, from the 2019 year, they also have a toolbox for interval type 2 in MATLAB, but before 2019 there was none there. So several toolboxes were developed around the world, and this was one of them that we, in our group, we programmed this to do our papers and our research, and we also provided to some other groups in the world. So you can define your membership functions with the parameters. And this is for the shower control benchmark problem, the rules, and then we can simulate, and we can see that even in this shower control, which is very simple problem, even in this case, we can have type 2 with lower values, lower errors than with type 1. Recently, we have also some work, like I was saying, on the theoretical part, because we have been working on trying to do type reduction with direct formulas, like in some, using as basis some previous work of other researchers. So this is one of these works. We have also done application of these fuzzy systems for adapting parameters in metaheuristics. Like I will just quickly show you one of these applications in a few slides ahead. We have studying the robustness of the controller when we use type 2. In some sense, the robustness is achieved because we have like many type 1 fuzzy controllers being used at the same time, and we have one type 2 fuzzy controller. So these embedded type 1 fuzzy controllers are like having many for different parameterizations, and so is, in some sense, we claim that this is why we have more robustness with type 2. And also more recently, we have tried to use shadow sets. Shadow sets are allowing us to reduce the number of alpha planes needed to approximate a general type 2, and we have done application of that in control. And a method for integrating, basically in general type 2, we approximate, one way to approximate is using alpha planes similar to alpha cats, but in this case, produced planes. And we can integrate the alpha planes using like a Newton codes integration rule, similar to numerical analysis. And we have done that in that paper. Another is to use construct general type 2 fuzzy sets is to use like a sampling with data, and we construct many type 1 fuzzy sets to in some way then cover these many type 1 fuzzy sets to form or to construct the general type 2 fuzzy sets. We have also done that and make an application to diagnosis. And this is also to construct the best shadow type 2 fuzzy system using particle sum optimization also. Like I was saying, optimizing is needed to have the best fuzzy system at the end. In type 3, basically what we do in type 3 is at the moment what we have done is to use in the secondary membership, instead of having a type 1 function, using in this case an interval type 2. So the secondary membership is an interval type 2 fuzzy set, and so in some way we have now an interval type 3. Not the full type 3 or general type 3 that we will call it. If we use a complete type 2 as a secondary, then we will have a complete type 3 fuzzy. Let me show you the plot. So in this case, we are using to construct the general, the type 3 fuzzy set. We are using secondary membership functions which are interval type 2. And so in this way, this is considered in this way. And of course, what we are now dealing is with the quickness or the making this computation very fast. We have some control applications of this. This is a setup. This is with some colleagues from Iran. Ardashir is one of my colleagues from Iran, and he has done some papers on this. And we have others being on review at this moment. But at the moment, not many papers on type 3. But this is an interesting way to go in the future. So let me see how much time I have. So a few minutes. So just I will show very quickly. This is an example where we have used the fuzzy system to control the parameters of the B-colony optimization algorithm. So the alpha and beta parameters that are used in B-colony, we have a fuzzy rules to control alpha and beta to make B-colony faster and improve results. And my student then, she did apply it to optimize the controller of our robot. So actually what she did in her PhD thesis was to develop this fuzzy B-colony with type 2 fuzzy system. And she applied to find the best controller for a robot, autonomous mobile robot. So I will skip some details, but basically this is the B-colony algorithm inspired on the bee's behavior to find food. And what we did is to develop this fuzzy system, fuzzy rules to control the B-colony based on by moving the parameters. Usually when we apply this method, the alpha and beta parameters remain fixed, a particular value that the user decides to be alpha and beta. But in this case, the alpha and beta will be changed dynamically during execution. These are the general type 2 fuzzy sets that are used, and the alpha planes that I was mentioning, we cut the three-dimensional form of the function, like slicing on horizontally. So we have, you can see here, when we cut, we have interval type 2s. So that's why we have more calculation, because each plane is like an interval type 2, and then we do the union of many of these alpha planes to approximate the general type 2. but we want to use as less as possible so that the calculations are faster. And this is the controller of the mobile robot, two-wheel mobile robot. I will show the schematic. And we are using the error in linear and angular velocity to control the two wheels in this case. And this is the kind of robot that we are dealing with. And these are the equations of B colony. Here we can see the alpha and beta parameters, usually are between values of 1 and 5. But if you leave fix these values, then the algorithm can be very slow or cannot give the best results. So basically, we need to be changing these values around, during the execution to make faster this method. And we use the iteration that we are at the moment and the diversity, which is basically measured as the difference between all the elements in the population, the bees in this case. So if they are very far away, we are maybe far from the solution. And when we converge, usually the bees are converging to one solution, and diversity is low in that case. So what my student did was she developed, based on this input, iterations in diversity, she developed rules to find the alpha and beta. She experimented a lot to see the behavior of the bee colony. And this is with interval type 2 and with general type 2. And she defined these fuzzy rules based on if we are at the beginning of the iterations and diversity is low. For example, beta is high and alpha is low. But then with the classification, we obtain a particular value of beta and alpha and so on. But this is calculated in each iteration to move alpha and beta in the best possible way. Like if we manually, we could try it. This will be the rules that an expert, in this case, she did become an expert on controlling the bee colony, and she put the fuzzy rules in the program. So the bee colony is changed by updating alpha and beta in each iteration with this fuzzy system. And basically, then she compared bee colony with fuzzy, type 1, interval type 2, general type 2, all against the original bee colony, and also bee colony with random values assigned to beta and alpha. You can also do that to be changing these values, and the results can be improved even with that. But then compare with bee colony with fuzzy. And these are some of the simulations. The red is the desired trajectory. The blue one is the one obtained by each of the bee colonies. This is without noise. This is for the original method. This is for random. This is for, this is the original one. This is with general type 2, which is, of course, this is one of the simulations, because usually in this case, we perform many simulations, at least 30 simulations, because we need to compare statistically the methods, the meta heuristics, to just really be able to say that one of the methods is better than the other. And so, but one of these designs, one of these was this one, and was the best one here. The actual trajectory, the robot is almost overlapping over the robot, the desired trajectory. And numerically, we can compare, here's the lowest value here with 0.04 error. And this is the convergence of the method. When we have noise perturbations for the robot, then we have that the trajectory is not so smooth, but the robot is trying to follow the red signal, but it's having perturbations, so that's why it's behaving like that. With type 1, we have like this, is lower error. Then with interval type 2, and with general type 2, of course, the lower error. So that's just a way to show that this is improving the behavior of bee colony in finding the best controller to control the robot in this case. And we have also extended that to these kinds of robots, which are more complicated because are like they are not with only 2 wheels, and also they have a translation. They can move in many other degrees of freedom. And when I cannot show because of time all the details, but I will skip. These are the models, and we have the type 1 controller using the sensors. We have 4 sensors in this case, and the type 2. This is the structure of the control using these 4 sensors, and to obtain the values for the robot in this case. I will skip and show you. These are the functions, the rules. This is the way that it avoids obstacles. And these are the trajectories that in simulation you can see, and then the real robot. And just to summarize here, we have faster for doing a particular circuit here or path that we want to follow. Then with type 2, interval type 2, the time needed to move around is less than with type 1, and also the error with respect to the desired trajectory is lower with type 2 than with type 1. So just to show that, and that this is an improvement, and this is not optimized. Now my student is working now in optimizing the design of the controllers to even reduce this more, because these are with manual or empirical design, just moving memory chip functions and values manually or by trial and error. So it's better to optimize both type 1 and type 2 and see the best behavior of both and then compare. So thank you for your attention. Basically, this is what I have because of time, but I hope that I have in some way convinced you that it's a worthwhile area of interest type 2 fuzzy. I'm only showing control applications, but as I said, my group has also in time series prediction, pattern recognition, medical diagnosis, and other areas, good results. So you can check papers on that also. And this is applicable to real world. And now we are going into type 3. Even some people maybe are skeptical, but the same thing happened about 20 years ago when people didn't want to go into type 2. Now we have maybe to go into type 3 for particular cases, some problems that need it. Thank you very much. And if you have questions, I don't know if there is time for questions.
Okay, may I ask a question?
Hocam sesiniz kapalı.
Yes.
Can you hear me now?
Yes.
Okay. Professor, thank you for the insightful talk. My name is Turan Sörmez from Istanbul Technical University. Actually, I'd like to learn a bit more about combination of this fuzzy control, especially type 2 control, with artificial intelligence, because we see some recent papers where they mix these two types of things together. So what's your impression on this type of approach? Thank you.
Yeah, actually, of course, I have focused more on fuzzy because of my research, but really, actually, for example, for an autonomous mobile robot, you can have that maybe part of the solution is solved with a neural network, another part maybe with another method, maybe the planning the trajectory. You need maybe you can use a genetic algorithm to plan the trajectory of the robot. So there are many parts of the problem, and the fuzzy system is like it will be like the decision-making module. Decision-making, like for example, when you are driving a car, the decision-making of having the rules to drive, like the knowledge to drive it, or when you have a helicopter, like in a paper like the one of Professor Atan, the knowledge of the pilots of the helicopter are then put into the fuzzy rules to control the helicopter or the plane or whatever system. So this is part of the problem, but of course, artificial intelligence or having an intelligent behavior requires maybe also neural networks or genetic algorithms or other methods. And we actually, in many cases, have hybrid systems instead of just having only fuzzy system or only neural network, because actually we are trying to simulate the human, and the human has many functions that some of them are more similar to a neural network and other ones are more to a fuzzy system. And also evolution is or other behaviors are also there. And these methods are like for part of the problem, not all the whole solution.
Thank you.
Thank you.
Is there any question or comments?
I want to ask a question. Can you hear me?
Yes.
Yes. First of all, thank you very much for attending our conference, Professor Castillo. We would really like to see you face to face. I hope our next meeting will be face to face. My question is, what's the biggest difference between type 2 and new generation type 1 fuzzy, for example, intuitive fuzzy? What's the biggest difference in practice you encounter?
The biggest difference between type 1 and type 2?
No, type 2, between type 2 and new generation type 1, for example, intuitive fuzzy.
Oh, intuitionistic fuzzy?
Intuitive fuzzy.
Between type 2 and intuition fuzzy. Well, the difference is in the way that we manage the uncertainty. In intuitionistic, what we have is that the uncertainty is represented by the use of non-membership function. So you have membership function and non-membership, and they are not complementary. So there is a difference between the hesitation margin is the part that adding, if we add the membership and non-membership, then it will give us the value of 1. So the way that this uncertainty is represented is by using this membership and non-membership and hesitation margin. And in this case, the uncertainty is considered on the membership. So you don't know exactly the membership, or you cannot give it a precise value. Then you assume that there is another membership function for every value of the membership. So that's different. So that's why they have combined both concepts. Right? As I told, for example, there is a very good paper by Professor Bob John in Transactions of Fuzzy about 2 years ago, 2 years ago, where they applied for prediction, but they have both concepts combined, because then you can assign secondary membership for membership and non-membership. I don't know if you get my idea. So it's like putting type 2 over intuitionistic, because you are not sure about the membership, so you can assign it a fuzzy value. And then you are also not sure over the non-membership, so you assign it a fuzzy. So you have like type 2 for the membership and non-membership. And so this is what they call type 2 intuitionistic, or intuitionistic type 2. So that will be maybe even a better model, because what some people claim is that the difference, in a summary for your question, the difference is that maybe intuitionistic captures some kind of uncertainty, and the type 2 captures another kind of uncertainty, another better, because you're using different things. But if maybe the problem has many kinds of uncertainty, different sources of uncertainty, if you use both, then you get better result. And I think that maybe that was happening in the time series prediction that they did, because they use a combination of type 2 and intuitionistic, and the prediction error was lower than if they use only type 2 or only intuitionistic.
Thank you so much, Professor.
Yeah.
Thank you
Okay.
so much.
You're welcome.
Is there any question or comment?
I can ask you,
Yes.
Professor, I wonder that what is the most difficulty for type 2 fuzzy to real system application?
For real system, well, for interval type 2 is not
Type
so
2.
much.
Type 2 fuzzy.
For general type 2, the complete model, the time, processing time is higher. So that's why we are finding other ways to approximate. For example, around 5 years ago, when one of my students was doing the PhD, for example, processing an image was taking 10 minutes. So you cannot use for recognizing a person because it was too slow in the computer. Now it's in seconds. So it is because we have developed other methods and better algorithms and also better computers. So, but it's still maybe some problems with more complication can take more time. So the thing is to have faster algorithms to compute all the things and real time, because we need very fast results.
There is a connection problem between Professor Özkan.
I think
he's unconnected now.
Oh,
Disconnected. I think there is no question anymore. On behalf of the committee, I would like to thank Professor Oscar Castillo for attending Congress at this pretty late hour. He is both a great researcher and a great mentor. I would like to express our gratitude to him personally for the direction and valuable ideas he has given to our works. It's a great honor, and it's a very good opportunity for us to know and meet you. I hope we will see him again in Turkey soon.
yes.
This is our certificate. This certificate is present to Professor Oscar Castillo for sharing his valuable knowledge and insights as a keynote speaker during Otomatik Kontrol Türk Milli Komitesi Ulusal Kongresi, which took place from 2nd and 4th September 2021 at Van Yüzyıl University, Van, Turkey. Thank you very much, Professor.
Thank you. Nice to see you. Bye-bye.
Nice.
Thank you, Professor. Have a nice day.
Thank you. Bye. Bye.
It's time to sleep, Professor.
Yes. Okay.
Thank you.
Thank you. Bye.
Thank you very much. Sayın hocalarım, saat 11'deki oturumumuz zaten biraz gecikmeli olarak başlamak üzere. İsterseniz oradan devam edebiliriz. Ve salonda